Okay, hello everyone. We're gonna wait maybe a minute because I see that the rate of participants, the number of participants is increasing fast, and then I will introduce Atac Imamoglu and we'll get started with the first lecture for today. Okay, maybe let's get started. So it's a pleasure. I'm Pablo Jarillo Herrero from MIT. I will be chairing this morning for me, afternoon for you session. And it is a pleasure to get started with Professor Atac Imamoglu from ETH Zurich. Atac did his PhD at Stanford, then spent some time as a professor at the University of California, Santa Barbara. And then he moved to ETH Zurich, where he leads the quantum photonics group. And I'm a great fan of Atac's work, so it's really my pleasure to introduce him and to give you the floor, Atac.
Okay, thank you very much, Pablo, and thank you to you and all the other organizers for organizing this event. I've really been enjoying it a lot, and I think it's a great idea to have this online and have it accessible for so many people. So for those of you who have been following the talks, so you know that the emphasis in this workshop has been on studying strong correlations between electrons and using transport spectroscopy. So I will try to give you a different way of looking at strongly correlated electrons, and that is using optical excitations, which we term excitons. So before I proceed, I'd like to thank my co-workers, and in particular, Yuya Shimazaki, Ido Schwartz, and Clemens Kuhlenkamp, who not only did the majority of the work I'm going to tell you about, but also helped me prepare some of the slides. And certainly without the HPN samples from NIMS, the work would not have been possible. I would also like to acknowledge theory discussions, collaborations with Yang Zhang and Liang Fu from MIT, and Michael Knapp and Richard Schmidt from Munich. So I'd like to start out with giving you the principal take-home messages. So in case I lose you during the talk, so basically there are two principal messages that I want to convey. The first one is a new sort of system, a new twisted heterostructure, which I could call a twisted trilayer, which consists of a monolayer of hexagonal boron nitride embedded or inserted in between two identical TMD monolayers. Okay, so this, I believe, has several interesting features. I wouldn't call it advantages, but several interesting features, because it does lead to a moiré superlattice, but with an important distinction that because of the HPN, the two layers are relatively weakly coupled and leads to a relatively weak moiré potential, such that the Coulomb interactions become the dominant energy scale. And moreover, in such a structure, both layers are identical, both TMD layers are identical, as you will see, and we can really think of a layer pseudo spin degree of freedom, which can be tuned basically by applying an electric field. And this essentially gives us an important tool for investigating the system. And the second aspect, naturally, is the fact that electron-exciton interactions in 2D materials allow for a local optical investigation or local optical spectroscopy of strong electronic correlations. And as I mentioned, this is the main message that I'm going to convey to you. So the brief outline, I will start out with elementary optical excitations of transition metal dichalcogenides. And here I will benefit or rely on the very nice talk given by Xavier Marie last week. So I very much hope that you have tuned into that. After this brief review, I will talk about exciton-polarons, quasi-particles or elementary optical excitations in the presence of itinerant electrons. Okay, so and I would try to convince you that these exciton-polarons provide a nice probe of strong electronic correlations in this trilayer, twisted trilayer structure. And then in the last part, I will tell you more recent work where we identified a relatively simple and a very direct optical signature of the Mott-Wigner states. That is an optical signature that emerges when the electrons arrange themselves into a periodic lattice. So let me start with some background comments. So basically, this talk is about optical excitations in the presence of itinerant electrons or holes. And as many of you would know, this is a very generic system with a long history. And the history goes both to pure physics, namely Fermi singularity, which is one of the first many body effects that we learn about when we study condensed matter physics, as well as very applied physics, that is semiconductor lasers or LEDs, which is all about generation of light or optical excitations when we have electrons and holes in the system. Now, so even though this is an old field, there is a new angle provided by the two-dimensional materials and their heterostructures. And the first and foremost of these is the fact that because of the reduced screening and relatively heavy mass of the electrons and holes in the system, the excitons are very strongly bound. And strong in this case means the binding energy exceeds 200 millielectron volts, even when the material is embedded in HBM, right? Okay, so this compares to gallium arsenide, where the exciton binding energy is between 5 and 10 millielectron volts. So what this strong binding means is that when we introduce these excitons optically by photon absorption, they act as a rigid mobile impurities in the Fermi sea of electrons or holes. Okay, so the other important advantage is that through top and bottom gates, we can control the degeneracy of both electrons as well as excitons. So electrons, we can basically apply a gate voltage to tune the density all the way up to 10 to the 13 per centimeter square, and excitons by increasing the intensity of the laser field. Okay, so this actually has the potential to lead to a very interesting regime of Bose-Fermi mixtures, bosons being excitons or polaritons and electrons being the fermions, and with the added twist that the bosons are dissipative, so they have a short lifetime. So it's a many-body system which is out of equilibrium and can only be studied under under an external trap. Okay, but the last angle is that because of the interactions between excitons and electrons, then we can use the optical excitations as a probe of electronic correlations. And this is what I will focus on in this talk, as I mentioned. Okay, so again, the part about the TMD monolayers will be relatively weak, and I guess many of the details that Xavier has talked to you about is not relevant, or at least as far as I can judge. So the main thing that we should keep in mind is that the lowest energy conduction and highest energy valence bands are in the high symmetry K and minus K or K prime valleys in the Brillouin zone. And the system has characteristically strong spin-orbit interaction, which means that in each valley, the lowest band is non-degenerate. So, and the spin-orbit interaction depends on the kind of TMD that one is interested in. But I will only show you data on molybdenum diselenide, where the spin-orbit splitting is such that the lowest energy conduction band and the highest energy valence band have the same spin. Okay, so which means that we can make optical excitations in between these two states, and we can observe the decay of bright excitons in the system. This is in contrast, for example, to tungsten diselenide. And again, as Xavier mentioned, the selection rules, and there's a typo here, this should be sigma minus, are dictated by the electron intercellular current, so basically are different in K and K prime values. So even if you do not know, haven't followed the optical experiments in TMVs, the main thing that is important, or the first thing that is important, is that if you were to look at the absorption spectrum of the system, which you can actually do simply by looking at the light that is reflected and send it to a spectrometer, you'll see features like the principal exciton line, and then the 2s excitons, and eventually a continuum. And somewhere in here would be an exciton, the so-called A exciton, and a B exciton between the spin orbit split bands. And again, our emphasis will be on the exciton, the lowest energy exciton. So the way to the first study, the quality of the materials, is to look at photoluminescence. There, the idea is to use a high energy laser to generate free electron hole pairs. These guys relax by emitting phonons, and the free electrons and holes correlate their motion to form a bound state, this exciton, the bound state of an electron and hole, which has this relatively large binding energy that I mentioned, and then could decay radiatively, provided that it has a small enough momentum, right? Because the conversion into a photon has to conserve momentum, and since the photons are so carry very little momentum, only the lowest energy excitons are allowed to decay radiatively. Now, if there are electrons in the system, and that's if you consider, for example, low density electrons that are unintentionally doped, then these excitons could actually correlate their motion with one of these electrons and form a molecule which is referred to as a trion in the community. So a trion is really, if you're familiar with sort of atomic physics, it is the counterpart of H- molecule. So it's really a bound state of an electron or two electrons to one hole, okay? And it turns out that there is only one bound state, and there is a singlet state, that is the electrons have to have opposite spin or Valley degree of freedom in order to be able to form a trion. Okay, and this trion has a very small oscillator strength, but since it's the lowest energy state, you will also see this in photoluminescence if you carry out such an experiment. Okay, so one nice aspect that Xavier again emphasized last week is that these the excitons, or these materials, their optical quality is extremely good. So good that basically the line widths that you measure, the best from the best samples, are basically of the order of their radiative decay rate. Okay, so this is by far not the case for gallium arsenide excitons, even those with the highest mobility. So what I'm interested in this talk are charge tunable heterostructures. So, and again, this is no sort of novelty to this audience because you've been hearing about these structures, but the basic idea is to encapsulate the TMD monolayer in boron nitride, and then have top and bottom graphene gates, could be few layer graphene. We don't want them to be too thick because we want to see the light through and look at the reflection, and then apply gate voltages to tune the charging. So I'll show you data from one sample where we had basically both a source and drain contact. And what we did is we measured both the source drain current dependence on the, in this case, the backgate voltage, as well as the spectrum, or the reflection spectrum, which gives us the absorption, the elementary optical excitations without having to go through this indirect path of photoluminescence. And what you see is that, of course, in the charge neutral regime, the current is vanishingly small. As we inject electrons, we see a current. As you inject holes, by lowering the backgate voltage, we again see the onset of the current. And correlated with these sort of onset of electrical current, we see two features. The exciton line, blue shifts and broadens dramatically. And there is a new resonance that appears at a lower energy, about trion binding energy away from the exciton, that essentially picks up oscillator strength as we increase the electron density or as we increase the hole density. Okay, so these resonances are termed by us and by Timkin and McDonald as attractive polarons, borrowing on the terminology that have been used in cold atoms for the last 15 years. Okay, so let me just show you a few lines of Hamiltonian and variational wave functions, just to convey to you sort of how one can understand the formation of these polaron lines and what their relation to trion, the molecular bound state, is. Okay, so the starting Hamiltonian is a very simple one. There is a density-density interaction between excitons and the electrons. The interaction strength, and this is a beautiful aspect, is determined by the trion binding energy. So we can use the photoluminescence measurements to determine what the molecular binding energy is, and we can then describe the interaction as an effective contact interaction where the interaction strength is determined by the binding energy of the trion. Okay, so in that sense, it's an experimentally motivated or determined Hamiltonian that we start out with. And the underlying assumption here, which is really important, which only keeps this description valid for low electron densities, is the rigid exciton assumption that I mentioned earlier. That is, even as we introduce electrons, we assume that the exciton remains a robust rigid object that binds an extra electron. Okay, so the way to get an approximate solution to the eigenstates of the system is to use what is known in the cold atom community as the Chevy ansatz. Turns out that these ideas were already developed in my community, and I wasn't aware of. This was by Suris in St. Petersburg. But the idea is really to use a variational wave function, the simplest non-trivial one, where you would write the wave function, the eigenstates, as a superposition of a bare exciton and a unperturbed Fermi sea, and another term, which is an exciton plus a Fermi sea whole pair generated on top of the original Fermi sea. We can also look at this as a trion whole pair, but I will not go into this. But let me just mention that such a sort of form of the eigenstate, which essentially is the form of polaron, can be understood as a coherent superposition of a bare exciton in the unperturbed Fermi sea and a collective excitation of many trions formed by all the electrons in the system. Okay, so we have one trion at a time, but we can the excitation can form a trion or has a probability amplitude for forming a trion with any one of the electrons in the system. Okay, so that's the distinction, if you will, between this polaron and the molecular state. The important aspect here is that this part, the bare exciton part, and in particular this quasi-particle weight, ensures that polarons have sizable oscillators.
So attached, there is a question. I will allow Massimo Tarelli to ask us.
Yes, can you hear me?
Yes, I can hear you well.
Oh, thank you. Well, sorry for interrupting. Your V of Q in the previous slide has an expression that seems to be independent of Q.
That's right. So that's the contact interaction assumption. So there is, actually my colleague Richard Schmidt have analyzed this problem in detail, calculated this, the scattering phases, and determined sort of how good this contact interaction approximation is. And it seems to work very well also for this problem, just like it does for cold atoms, right? I mean, of course, one should keep in mind that this, one has to normalize regularize this interaction. There is a cutoff, but in the end, when you calculate the relevant quantities, such as the T matrix, then this cutoff disappears from the problem, and you have a well-defined let's say, effective interaction strength and the spectrum.
Thank you.
Okay, so now again, a few points about, let's say, the exciton Fermi polaron. So we can also consider these as excitons dynamically screened by the itinerant electrons. Okay, so as I said, there are two features. There is the attractive polaron branch, and the exciton itself becomes a repulsive polaron. Okay, so the exciton also gets dressed or anti-dressed by the electrons. It sees an effective repulsive interaction due to the presence of a bound molecular state in the problem. Okay, so the bound trion state is crucial for the attractive polaron formation, so that's an important aspect. The vanishing electron density, if you go to the limit of having one electron per optical sort of spot, then clearly polaron has to merge into the trion. And the other aspect that is important if one were to study polarization properties is that excitons in one valley only interact or can only be dressed by electrons in the opposite valley. Okay, so this is important when one studies the magnetic response of the materials. That the attractive polaron has and can actually be narrower than that of the exciton because of the quality of these materials, that the radiative decay rate, which in attractive polarons do live longer, but because they do live longer, their alignments can be narrow. Okay, but now the important aspect for this talk here is really this very strong electron density dependence of the repulsive polaron. So this is what we are going to use in order to monitor the charging of a given layer also in a bilayer system. And clearly, I guess I should also mention here that if you have, even if you have two layers that are separated with, let's say, an HBN, the electrons, because of the contact-like interaction between electrons and excitons will only be sort of sensitive to the electrons in the same layer and the opposite valley of the same layer. Okay, so I should have probably noted that here because it is an important point. So how do we use this strong dependence? What we can do is basically monitor, and this is really a brilliant idea, in my opinion, at least by Yuya Shimazaki. So we can basically focus on the reflection strength at a given frequency. Say in this case, for this dispersive line shapes, you can focus or choose any point. And then what you will see is that this reflection contrast, as the electrons are introduced into the system, the line shifts to the blue, and therefore the reflection contrast gets low. So by monitoring these shifts, you can actually determine whether the layer is neutral, electron charged, or hole charged as you scan both the top and back beats. Okay, so at this point, of course, this is not terribly interesting because you also see have the same information by directly looking at the reflection spectrum. But it is important, as I will try to convince you, to be able to sort of indicate when we have electrons, even if we, at this point, we're not saying anything about the electron density. For that, we need to look at the derivative of the change of reflectivity. Okay, but that's the idea of a charge configuration for a monolayer system. So, that was the introduction. So now I'd like to introduce you to this trilayer structure that forms the basis of this talk. So as I already mentioned, so this consists of two molybdenum diselenite monolayers. Actually, they're obtained by by the technique that our chairman Pablo has developed here and stack. It's just that before stacking them and introducing an angle, we introduce a monolayer of boron nitride in between. So schematically, the structure looks like this, again with top and bottom gates, and then there is a monolayer HBN in between the two. Okay. Now it turns out our structure had a twist angle, which we inferred later on of about 0.8 degrees, which leads to a Moire periodicity of about 24 nanometers. Okay, and I must admit that all our information about these angles is from optical spectroscopy, so we don't have an independent way of determining what the angle is in this embedded structure. Okay, so this is now the last photoluminescence that I'm going to show you. So this is to characterize the whole structure, which of course has regions where we have this trilayer. There are regions in which you have a monolayer of molybdenum diselenide, and then we have regions where these dark regions where we have a bilayer molybdenum diselenide. And what is important here is that bilayer molybdenum diselenide is very dark, and that's something that the community has known for a while, because these 2D semiconductors have this remarkable property that only monolayer is direct bandgap. So as soon as you have bilayer or higher number of layers, then it's in momentum space indirect excitons that you deal with, which have a long lifetime and most likely are also subject to non-radiative recombination because of their long lifetime. So you do not really see them. But you see that the introduction of HBN renders this trilayer extremely bright, and that is basically telling us that this hybridization in that normally, for example, lowers the energy of the gamma valley is not effective here. We've reduced the tunnel coupling sufficiently that the bilayer system becomes direct bandgap, or trilayer system becomes direct bandgap, or remains a direct bandgap structure. So let's consider the possible excitons in this bilayer system. So roughly speaking, we have two possibilities. We can have an intralayer exciton, so that would be the same as in a monolayer, but we can also have interlayer excitons where the electron and hole reside in different layers. Okay, so this was again discussed by Xavier last week. And on top of that, we have this gate control, which allows us to tune the energy of the indirect and the direct excitons. Okay, so that's what we sketched here. So the direct, so I should say intra versus interlayer. Intralayer excitons have a stronger binding energy. We measured this to be about 100 millielectron volts stronger than the interlayer excitons, and that's simply due to the fact that there's an additional nanometer or so scale separation of the electrons and holes. But this energy difference we can compensate by applying a voltage and really bring the two guys into resonance such that the energy of a intralayer exciton becomes the same as that of the interlayer exciton. Okay, so if there is then some coherent tunnel coupling remaining despite the boron nitride layer, then we should see hybridization of these excitons. And this is indeed what we see. So if you look at these regions that I will highlight here, okay, so you see that this direct exciton line is hybridized into lines which have a very steep dispersion with gate voltage. And that's precisely what we expect, because for interlayer excitons, because of their large out-of-plane dipole, they couple very strongly to the electric field. Their energy is easily tuned, okay? So, and the other feature that I should mention here is that we see two exciton lines. So this is the top layer exciton, and this is the bottom layer exciton. So even though these were obtained from the same monolayer, because of the strain difference, they develop a different energy. And this actually energy difference varies through the sample and even changes sign on a different end of the sample. Okay, but this actually turns out to be very useful for us, as I will try to convey to you. So what is important here, though, is that we see that the top layer hybridizes on the positive gate voltage side, whereas the bottom layer hybridizes on the other side. So we do not have the counterparts on the for positive voltages on the bottom layer, etc. And this actually is due to the fact that we only have coherent hole tunneling strong enough that is larger than the decay rates for that is for holes. So the coherent tunneling is only strong for the holes, whereas for the electrons, this is, we don't know what its strength is, but we know that it's weaker than the exciton line. Okay, and this actually is something we kind of anticipated, because if you look at the DFT bands of HPN, you see that the conduction band offset is much higher than the valence band offset as compared to the molybdenum diacellide. So that is nice, but if you focus on these either of these two regions where we have either the top layer exciton hybridizes with interlayer or the bottom layer, we see that actually we do not have a single indirect exciton line with which hybridization takes place, but we see at least 3 of them on both sides. Now, initially we thought that this might also be due to some inhomogeneities in the sample, but this feature is robust. You see wherever you go on the sample, you have basically there are some variations in the energy splitting, but these features of 3, at least 3 indirect exciton lines are prominent. So we tentatively concluded that these are moire excitons, and this is actually by now an established field. We again heard about it last week. So the pioneering work, as far as I know, was due to Allen and Wang Yao, and the idea is that in a twisted structure, or in some cases even without a twist, because, just due to the lattice mismatch, we generate essentially interlayer excitons with the moire potential. And these interlayer excitonic potential can vary dramatically over the unit cell. Okay, and this is a theory prediction. I believe this is from Alan MacDonald, showing the new indirect exciton lines that one could expect to see. Okay, normally though, these indirect exciton lines in these sort of heterostructures have essentially vanishing oscillator strength, so you can only monitor these in photoluminescence, whereas in our case, because we're tuning the energy and hybridizing it with intralayer excitons, we also see it in reflection. Now, one important thing is, of course, you did the DFT calculation, and what we found surprisingly is that for us, the exciton energy variation should be very small. And this is not agreeing with the experiments, but that is kind of where we are. Okay, so now let me again go back and really focus on the electronic properties and using optics as a spectroscopic tool. So here I show 3 different basic sort of reflection scans obtained for different sort of correlated tuning of the top and bottom gates. And you see that the system becomes now extremely rich depending on what you choose for alpha and beta. That is how you change the top and bottom gates. You see all kinds of different sort of exciton line shifts in the system. Okay, and again, that the fact that there is this energy difference allows us to basically look at, or in principle, look at each layer separately. So so what we can do is apply the method that I've described to you before, and again change, obtain a charge configuration map of, say, the top layer by changing, scanning the whole region of bottom and top gates. And in this way, what we find is that there is a funny shaped neutral region, an electron dope region, and a hole dope region. And there's a corresponding sort of charge map for the bottom layer. Now, what we did is that we combined these two, and that resulted in this rather curious, at least to me it was, the combined bilayer charge map. So what you see here is that the neutral regime, where both layers are neutral, is separated from the layers where the regime where both layers are charged by this tiny region where the electron density is very low, and there is this very funny sort of rectangle-like structure, which is going to be the focus of the rest of this talk. Okay, so because the electron densities are low, so I rotated the sample now. So this is the axis now along which we change the chemical potential. So the electric field remains constant. This is the axis along which the chemical potential remains constant. Okay, and then we will look at this very low electron density regime and hope to see the strong electron-electron interaction effects. Okay, so now, so what this plot shows is how the exciton or repulsive-polaron in this case, resonance energy shifts as a function of chemical potential. As we increase, maybe I should use this cursor, as we increase the total electron density. And we differentiated with respect to chemical potential to be sensitive to the changes even after the electrons are injected. And you see something interesting already here, that there is a periodic sort of charging and even some decharging of a given layer, in this case the top layer, before the charging resumes. Okay, so so this actually can be carried out for both layers, and then we can combine the energy shift between the bottom and the top layer as a monitor of the charge imbalance or the charge difference of the two layers. And when we do that, what we see, these sort of periodic oscillations in the charging become very clear and nice. So basically, for electric fields, voltages larger than -1 volt, -1 actually in our structure refers to zero electric field. It's a bit confusing, but that's most likely arises from the difference in HPN thicknesses. So basically, here on the higher electric field regime, we first load electrons to the top layer, then we only load them into the bottom layer, then to the top layer, etc. So there is this periodicity in the electron doping. And the density of electrons that in each period corresponds to is about 2 × 10⁻11, and that is consistent with this 24 nanometer, or that directly gives us the 24 nanometer Moire period. Okay, so we will identify, so this is the regime then where we have 1 electron per Moire site. We will call this nucleus 1/2, taking into account the spindali degree of freedom, but basically 1/2 means 1 electron per Moire site of a layer. And nucleus 1 means 2 electrons per Moire site, where the electrons could be either in top or bottom, or both of them in the top layer. Okay, so I guess I should speed up a little bit. So one interesting plot that I'd like to show is that if I go to this single electron per Moire cell regime and change the electric field, so this is this data, you see that the electrons in this case, the bottom layer, remain where they are until the electric field is 0. And then there is a relatively abrupt transition of all the electrons to the top layer, such that the bottom layer now becomes a bare exciton without having any energy shift. This actually smoothens out either as we increase or decrease the electron density. And this is essentially the color coded plot where you see this jump. This here actually in this case, the steps were a bit larger, so it's not showing as smoothly as it really is. I will come back to this. But the important point is that these energy shifts directly give us information about electron density. If you look at the attractive polaron, then it's not the energy shift, but the strength is proportional to the electron density. So we have these two ways of looking at the changes in the electron occupancy. Okay, so now the question is, how can we understand this what I refer to as the resilience of layer occupancy with respect to the electric field at nu equals 1/2. Because normally, I mean, without interactions, you would expect that some of the electrons would get transferred onto the other layer, and there will be gradual transfer of the electronic population from one layer to another, rather than this abrupt transfer of all electrons in one go. Okay, so one way of thinking about it is really to think of the bilayer as forming a honeycomb lattice with two different sides. So in the A side, the metal atom of the bottom layer is lined up with the chalcogen atom of the top layer. So we assume that this is the lowest energy state of the electrons in the bottom layer. And the B side is the converse, where the metal atom of the top layer lines up with the chalcogen atom of the bottom layer. Okay, and this is the lowest energy side of the B level. Now, so the point is that if we have strong interside Coulomb interactions, then the transfer of an electron from A to B side could be energetically forbidden, even when the electric field is approximately 0, because such a transfer results in enhanced Coulomb energy cost. Okay, so this is what I will try to sort of depict to you with the help of this pseudo animation by Clements. So we have these two layers. Again, is the bottom. This pinkish is the top layer. We have a finite angle, and we see the Moire pattern appearing. And then we have these XM sites. Okay, so these are the sites in which the top layer has, sorry, in this case, the bottom layer has the lower energy, and the green-gray sites are the MX sites, where the top layer electrons have a lower energy. So, okay, so let's start out with say a Mott state. If we were to have a Mott state in the top layer, if an electron, so the electron cannot transfer to another minimum because of this displacement of the two to the potential minima, and if we have these electrons in, say, in the top layer, and if one electron were to be transferred into the bottom layer, then it will have to pay an extra energy, interaction energy cost, which can be calculated in this way, where V1 is the nearest neighbor interaction, V2 is next nearest, etc. So this is what Liang Fu refers to as a charge transfer exciton, right? So basically, by moving an electron from one side of the honeycomb to the other, you generate a dipole, an exciton, and this exciton has a finite energy cost, okay? And this finite energy cost is responsible for suppressing such single electron or few electron events. But naturally, if all electrons were to go from the top layer to the bottom layer, then the energy is the same. So in this way, we can understand why the system acts in this very robust, let's say, layer ferromagnetic fashion. Okay, and this is now a finer scan of the electric field, and you can see that indeed at nu equals 0.5, the top layer, let's say, energy shift abruptly increases, and while the bottom layer energy shift abruptly decreases. What is remarkable here, and this is what we tentatively attribute to a Mott insulator being in one layer that is stabilized with intersite interactions. Okay, what is really remarkable here, though, is that if you increase the electron density, what you see is that even for larger electric fields, in this case of the bottom layer, decreases below that of 0.5, what we have at lower electron densities. Okay, so it looks like it has become energetically favorable to transfer the electrons from the bottom layer to the top layer as we put more electrons. I would also like to emphasize these plateau-like features that we see as we move away from this multi-insulator state. So how to understand this? So this is where Yang and Liang come in to play. So this was really motivated by Liang's very nice colloquium a few months ago. So basically they consider trimer states. And so what they predict, this is for our system parameters, is indeed that this transition, as you move away from the nucleus 0.5, the single electron per Moire site, to higher values, then the electrons will be transferred from one layer to another, in a sense, a bit prematurely, even though the electron density is high. And the way they understand this is via the formation of a trimer, or if you want a tetron. So where the idea is that if you want to have, let's say, we inject additional electrons, in this case, say to the bottom layer. So these electrons can lower their energy by generating a dipole, by generating a charge transfer exciton, by moving one of the electrons in the top layer also to the bottom layer. And this complex of 3 electrons in the bottom layer plus 1 hole in the top layer actually can have negative energy. And in this way, one can form a bound state of charge -2, which again, at least I find very interesting. And this is, so basically in these plateau regions, when Yang did his classical Monte Carlo simulations, he saw that I believe about 90% of the electrons are accommodated in these trimer states that you see in the bottom layer, okay? So that's what we'd like to do now, is to go to lower temperatures and really sort of try to see if we can actually match the plateaus well, and also determine what these interaction strengths are more precisely. Okay, so let me, in interest of time, let me go to this last part, the direct signature of mode state of electrons. I've been telling you about mode state and indication, etc. But the bottom line is this, that if there is a mode state of electrons, or if you didn't have a Moire potential, if the electrons were to form a Wigner crystal, spontaneously breaking translational invariance, then the excitons, due to the fact that they interact with electrons, will now see a periodic potential. And this periodic potential should result in the formation of exciton bands that one can analyze in a sense by extending the Kronig-Penney model, because basically I've argued that the exciton-electron interaction can be treated as a contact interaction. So now that we have localized electrons in a lattice, then the excitons will now see a periodic potential due to this. And this should result in the Umklapp peaks, or appearance of new resonances. And this is precisely what we see. So in this case, again, going back to this nucleus 0.5, what you see is that as the electrons are injected, in this case, to the top layer, you see that there is a new resonance appearing about 2.7 nanometers above. And similarly, for the bottom side, when the electrons are on the bottom layer, there is a resonance which is weaker, but has almost the same energy, about, in this case 2.6, shifted away from the exciton resonance. If you go to the nucleus 1, in the regime where both layers accommodate a mode state with 1 electron per site, then we see these Umklapp peaks in both layers simultaneously. And this is actually what happens when we change the filling factor and go from, let's say, no electrons to single electron filling of the bottom layer, or let's look at this one, single electron filling of the top layer, then to single electron filling. So in this case, we are really taking an electric field scan, an electric field value of about -0.8 or so. Yeah, -0.8. So it's around this value. Okay. So, and we change the chemical potential. So what you see is that as soon as we hit a single electron per site, nothing happens in the bottom layer exciton, but Here the unclap peak emerges, then disappears, and then appears again for n equals 1. Okay, and then there is this energy shift of the exciton, which our model also explains. So the model at this point is very simple. It's actually, we think it's a rich theory problem, basically dressing of excitons by collective excitations of Mott or Wigner state, depending on the context that one is looking at. This theoretical analysis assumes the simplest possible scenario, saying that, okay, we'll just look at the mean Hartree type term. So we start out again with density-density interaction between exciton and electrons, but replace the electron density with this periodic potential. And the interaction strength is fixed by the trion binding. And what we indeed see is that there are, in addition to the attractive polaron and the exciton, which blue shifts, we see an additional unclap band. And for our model, we find 3.1 millielectron volts, which is larger than what we measure, but it is consistent. So the dashed lines indicate here the light cone. So only, as I mentioned earlier, small momentum excitons can be converted into photons. So these are the guys that we see, and the oscillator strength of all these other unclap bands actually vanish at k equals 0, and therefore we only end up seeing 1. And that's indeed what happens in the experiments. Okay, so an outlook of this is, now we have a tool that actually also allows us to look at, say, correlated electronic states without a Moire potential, even at in a monolayer. And that's something we're looking at for Wigner states. So I emphasize that this is a local sort of spectroscopy of correlated states. Our resolution is about a micron, but this can be improved by using near field techniques down to about 50 nanometers. And again, what is exciting is that our experiments have hints of the formation of trion states, which will then, of course, be very interesting to see if they lead to superconductivity in one layer, or whether they will actually, at low enough temperatures, form Wigner crystals. So these we do not know, but want to investigate with you. Okay, thank you for your attention.
Thank you very much, Atac. So we actually have quite a bit of time for questions. Anyone wants to get started? Let me see. I'll go to the list and okay. Someone, I see that someone raised their hand. Let me see.
So I read Maximilian Kögel on my screen.
Yeah, let me, I don't know why, usually okay. Maximilian Kögel, you're allowed to speak now.
Yeah, thank you for the talk. I have a question about the animation you showed about this collective, I would say, tunneling between the layers that you showed for the MOSE2, top MOSE2 to the bottom MOSE2. Mm-hmm. You said that due to that all of the electrons would need to get to another spatial position to kind of get down to the bottom layer, which is because of the Moire potential. Mm-hmm. But I think the Moire potential, isn't that something that happens due to the, which has to be seen as from the double and of the top and bottom layer together?
Yeah, so that's actually, thank you for that question. So that's really an important difference, as far as I understand, between the twisted bilayer graphene or the heterostructures, TMD heterostructures, twisted heterostructures that people have investigated. So basically, because of the large tunnel barrier, or the tunnel, the HBN in between the two layers, the tunnel coupling, particularly for electrons, is can be neglected to first order, right? So that means that there is virtual tunneling events that result in a weak potential. And I emphasize that the potential is actually weak compared to the Coulomb interaction scale. So we're not really in the Hubbard model limit. I mean, it's really an interaction dominated regime, but we have this potential nevertheless, right? That provides essentially a pinning, if you will, of the Wigner crystal. And this minima, the weak minima, occurs at, let's say, the site of the metal atom, or the site in which the metal atom lands on top of a chalcogen atom in the other layer. So let's say for the top layer, if the metal atom in the top layer is over the chalcogen atom of the bottom layer. And it's the other way around for the bottom layer. So that means that these two potential minima are displaced from each other in space. Okay, that's why we do not have a triangular lattice, but we have a honeycomb lattice where the electrons, the lowest energy single particle states are not at the same energy. So you can think about an A site being an electron, say, in the top layer, and B site electron in the bottom layer. Maybe I use the other notation, but and this energy difference is tunable with the electric field that we apply, right? Because basically the electric field changes the relative energy of these guys. So that's what I meant by this tunable layer pseudo-spin degree of freedom in the system. Is that, was that?
Yeah, that makes things very clear. Thank you. Thank you for the explanation.
So, Pablo, I see two questions on the question and answer. Should I try to answer?
Sorry, I was muted. Yes. So there are two questions in the question and answer. So maybe we can let the speakers themselves ask it. Okay. If you want, Beata, you can ask your question.
Okay. Can you hear me?
Yes, I can hear you.
Okay, I have two questions. One is very simple. I'm quite puzzled that in your reflectance spectra, there is fair range of voltages when the layers remain undoped. I would somehow expect that this range will be a bit smaller.
Yeah, so I think yeah, go ahead.
My second question is related to the polaron picture. The Moire potential seems to be fairly large compared with carrier concentrations where the Fermi polarons appear, and yet you use the same language, I guess, to describe the problem. So I was wondering if you could comment on that.
Mm-hmm. So yeah, so the first one, I must say, I mean, I have a quantum optics background, so I'm not sure if I completely understand, but my understanding is this extension of this neutral plateau beyond the quasi-particle band gap is due to the fact that we do not have good contacts in our system. So that basically means that from depending on the sample that we are dealing with, the extent of this neutral region can be very different. And there's also devil is in the details. So it's not even clear if this neutral regime is always completely neutral. So it looks as if, at least in a sizable fraction of the samples, basically we do have about 2 volts of no trion emission, right? And then for, let's say, about 8 volts where we see weak whole trion emission. So it looks as if there is either there are defect states close to the valence band, or that the whole injection is sort of partially hindered. We can inject some holes, but only very slowly, and then it turns on abruptly. So we do not understand, but I think that it's most likely, I would say, is due to the whole context, that is our inability to efficiently inject holes into the system. I want to show you one graph here where, So you see, I mean, here you do not see in the small hole doping because of the fact that this is reflection. If it were emission, you would see that the real neutral regime would be somewhere here, and then you're going to see PL here. And you see the other sort of reason why we attribute this to contacts is that with gate voltage, there is a nice sort of smooth increase of the repulsive-polaron energy on the electron side, whereas it looks like we very sort of the rate at which we inject holes is much faster. So this doesn't make sense. I mean, given that the electron and hole masses, etc., these guys should behave rather symmetrically. So, so that's my tentative explanation, but maybe there is more refined ways of answering these questions. So your second question was regarding the validity of the Fermi-Polaron model. I would say that I feel quite comfortable because particularly in this sort of low sort of electron density regime, we're really talking about 2 × 10⁻11 electrons per centimeter square. So here the Fermi energy is more than an order of magnitude smaller than the trion binding energy. So at this point, I think the Polaron picture is very much valid. There might be interesting issues like actually the molecular energy being lower, the trion energy being lower than the Polaron energy, which might complicate photoluminescence. But since we deal with reflection, this is a non-issue for us.
Thank you.
Okay. And I can see that we have also Yadong Wang. So I'm going to allow you to talk, Yadong. You can ask your question. I'm going to unmute you. So, okay. Yadong, are you there? Would you like to ask your question?
So maybe, you know, in his note, Pablo, he says that he doesn't have the headset. I don't know if...
Oh, okay, okay.
So what he said is, yeah, now he says mine is not working. So his question is, how does the strength of the interlayer exciton compares with the normal exciton? So, so what we can actually, from the gate voltage dependence of the interlayer exciton, we can determine what this binding energy is with relatively high accuracy. So we cannot determine with these experiments what the actual binding energy is, or I should be more precise, but we can determine what the difference of the binding energies is. And it's 100 milli-electron volts. And other colleagues have measured the binding energy of moly diselenite in HBN, embedded in HBN, to be around 200 to 220 milli-electron volts. So that suggests that it's about 100 to 120 milli-electron volts.
Very good. We have still time for a few questions if anyone is interested. Okay, Kemal Atalar has a question, and I'm gonna try to let him speak. So let's see, Kemal Atalar, you are allowed to ask your question if you want.
Hi, can you hear me?
Yes.
So I was wondering if you have studied other TMD chemistries in your setup, such as tungsten disulfide, let's say. Do you expect to see a similar physics, or what differences or similarities do you expect?
Yeah, so the answer is no, we haven't. I mean, it's clearly one of the next steps is to try a similar structure with tungsten diselenite. As compared to sulfides, there is a practical advantage of selenites. That is, they emit, or their resonances are about 700 nanometers, which means that that's where our light sources are, right? So that makes the investigation easier. And tungsten diselenite has some interesting properties that we do not, or at least I do not understand. And how this shows up or couples to the interlayer physics and the Coulomb interactions would be interesting to see. But the short answer is no, we have only looked at molybdenite so far, which, I mean, there is one advantage of molybdenite. It is, as far as I know, still has the narrowest exciton lines, right? So since we're doing optical spectroscopy, there is benefit in dealing with the narrowest energy excitation such that we have the highest resolution. And these, by placing them in cavity-like structures, one can even reduce the lifetime and reduce the, prolong the lifetime and reduce the line width. And this is probably the way to go if one is interested in just focusing on strong electronic correlations.
That makes sense. Thank you.
Are there any more questions? Okay, I think.
So 2 hands.
Yeah. Well, okay, one hand went and disappeared, the other one too. I guess those may have been mistakes, accidental hand raisings.
Okay.
Okay, no, actually, Maximilian, do you have another question, Maximilian?
Yes, I have another question. Thank you. I don't want to give the opportunity not to other people, but when you zoomed into this anti-crossing of the hybridization between the interlayer and the intralayer exciton, you said that you have seen 3 different lines, which you attribute to the Moire potential or Moire excitons. Why is it? I don't understand that point. Do you mean that those originate from the 3 different positions in the Moire unit cell, or can you explain it again?
So basically, I mean, the way I understand it is that indeed that we have a potential, right? So this and this potential results in the formation of different excitonic bands. So these are, I mean, they can be localized. There has been a discussion of whether one can actually use such landscapes or potential landscapes to generate 0-dimensional emitters. But at this point, with our excitation, we are creating excitons. So these are basically collective excitations of many of these spots. And it is also not clear to me how well localized, if I consider an exciton corresponding to any one of these branches, right? It's not clear to me how well they are localized into one of these high symmetry points, their wave functions. My guess is that they're extended. And what is important here is that, and I think this also was the case in Allen's and Wang Yao's calculation, is that interlayer excitons typically or generically see a stronger potential variation than intralayer excitons. So we have almost no very faint indication, only in resonance fluorescence data that we see that I didn't have time to show, some indication of a sort of an umklapp band for an intralayer exciton. But for interlayer, this is much stronger, and that again is as far as I understand, is a generic feature in the system. But again, it's not really, one shouldn't really say that, oh, the exciton is localized at this point. That would be a quantum dot, right? So, so clearly we have a superposition excitation of these guys, and probably the wave function extends out, and therefore basically it has a finite oscillator strength with the intralayer exciton. But the devil is in the details. I mean, maybe the fact that this intermediate resonance is stronger could be due to the fact that that has a stronger overlap with the intralayer exciton. So since we are not really a DFT group, I mean, I've never done DFT calculations myself, and Yuya did in our case. So it's not clear to me how accurate we can be in making these predictions. So that's why I'm trying to be tentative in my sort of assignments or descriptions here. Is that?
Yeah, thank you very much. Yeah.
Okay, we still have a couple of minutes, actually more like 5 minutes if anyone wants to ask a question. So let me see. Maximilian, do you have another one? I see your hand raised again, or is it from before?
Oh, no, it's still from before. Sorry for that.
Yeah, okay, sounds good.
So I see a question here in the question and answer.
Oh, that's right. Dibao.
Dibao.
Let me go to Dibao and allow him to. For some reason, I think they come with a little bit delay to me, you know, across the Atlantic or something. I don't know. So allow to talk. Dibao. Di, would you like to ask your question? Di, can you?
Sorry, can you hear me?
Yeah.
Yeah. Okay. So I have a question about the picture of Fermi polarons or your trions. So basically, I believe you are talking about like a low doping regime, right?
Right.
So I'm wondering if you like your doping level is above that. Far above that. The picture, the regime that the Fermi polaron or trion picture can be valid. So basically, I saw some paper that proposed the exciton plasma picture. So what do you have any comments?
Yeah, so I do have comments. So so basically, the way we think about it is that so there are two regimes, right? So the plasma frequency of the electrons is getting to be comparable to that of the exciton binding energy. Then this whole formalism breaks down. And the reason for that is now the electronic electrons can follow the excitons and can efficiently screen the electron hole attraction. At that point, the exciton binding energy should decrease dramatically. So at that point, the description would be very different. Maybe we will go into more like a, well, not exactly Fermi singularity, but Fermi singularity-like regime where the hole is mobile. Okay, so then, so as you say, we are interested in the regime where the electron density is very low. And then there is this intermediate regime where the electron, the Fermi energy could be comparable to the trion binding, but still the plasma frequency or plasma energy, plasma frequency much less than or sizably less than the exciton binding. At that point, it is, we thought that it would be possible to capture the physics by, instead of considering these electron hole pair excitations out of the Fermi sea, by basically consider plasmon dressing. So to argue if it would be, one could get a good description by using sort of a bosonic dressing, if you will, by sort of virtual excitations of plasmons. At low density, we didn't succeed. I mean, so up to about 10 to the 12, the calculations did not match, but we didn't push this so hard. So I would say that in principle, what your comment is a very good one, that in an intermediate density regime, it should be, at least to a good extent, describe the dressing of excitons in terms of plasmon excitations.
Okay, thank you.
So we have an anonymous question, so I'll read it. Do you have a simple explanation for the Moire lattice to be honeycomb and not triangular, as for twisted Bilayer graphene? I will mention that twisted Bilayer graphene is actually honeycomb, but in any case, Atac, why is the Moire lattice honeycomb and not triangular?
So let me have another go on this, that again, the picture that we have is that each layer actually has a triangular potential, but when you consider the two layers together, and really consider this layer degree of freedom, the potential, these two, let's say, layers are shifted with respect to each other, such that the overall electronic potential, when both layers are taken into account together, has a honeycomb lattice.
So maybe I can add, what would happen if instead of 0 degrees, near 0 degrees twist angle, you would use a near 180 degrees twist angle?
Yeah, so then I guess the main effect is that because of the spin sort of mismatch, the interlayer excitons would become basically dark. But I don't think that this is a showstopper. I mean, I'm not sure. I must say I haven't thought about what the implications would be for the Mott states, but yeah, I can't think of any.
Okay, let me see. There was a hand before, but I think the hand went down. Are there any other questions? Okay, this is perfect. Okay, Beata, would you like to ask a question?
If there is time, yes, please. This is related to the intermediate doping regime that you mentioned just a moment ago. That in this regime, you would expect that the correct picture would be an exciton dressed with plasma excitations. What would be the experimental evidence for such a state?
Yeah, I don't know. I mean, I think that basically what I would do is, if I were to develop a reliable theory, I will try to measure the line shifts and the oscillator strength transfer and try to see if we can match it with by, instead of considering arbitrary particle hole pair excitations, by whether we can match the attractive and repulsive polaron energy differences using this bosonic dressing. So that's what I would do. I mean, I don't really expect a drastic, different experimental signature, I must say, but I might be wrong.
Thank you.
Okay, so it's time to conclude. Thank you very much, Atac, for this wonderful lecture. Thank you to all the participants. And we're going to have now a short break before the next lecture. So again, we thank Atac again. Thank you very much.
Okay, thank you very much. Thank you, Pablo. And I will see you in the next seminar. I'm going to end the meeting now. Bye-bye.